Hello learners, welcome to this course on Embedded System Design using AT89C51 Microcontroller. So in this tutorial, I will be discussing about on how to configure and program your UART, which is available in AT89C51 Microcontroller. So a UART stands for Universal Asynchronous Receiver Transmitter. So this is a serial communication protocol. So thereby we can transmit the data bit by bit. So it is a dedicated hardware which is going to do this operation, bit by bit transmission. So and it is asynchronous in nature, which means the data transmission is not synchronized with the clock signal. So here the data transmission happens with respect to different baud rates. So baud rates stands for number of bits transmitted per second. So it supports different baud rates, different data rates. And also it supports different data formats. Like we can do a 8-bit transmission in a packet, or we can do a 9-bit transmission in a packet. So we'll be sending the data as a packets. So here the number of data bits in the packet can be varied, 8-bit or 9-bit. So here if we see the UART communication, so this talks about only the protocol, the format of your data being transmitted and also the transmission rates. So whereas the signals or voltage levels in devices vary with each other. So for example, in case of a microcontroller, a logic 1 is represented by a 5 volt, logic 0 is represented by a 0 volt. Whereas in case of a computer, there the logic 1 is represented by minus 12 volt and logic 0 is represented as a plus 12 volt. So here, even though the logics are same, 1 and 0, the corresponding voltage levels in the devices is going to change. So thereby we need to have a driver circuit which handles this electrical signaling levels between the two circuits. So for that we will be using an IC called as MAX232, which is a driver IC. So which will be used for handling this electrical signal levels. And the main applications are, we can transmit the data from a microcontroller to a computer, or from a computer to a microcontroller, or to devices like mouses, monitor, printers, projectors, etc. So if we see, if I have two devices which has an UART, so it has basically three lines: transmitter, receiver and ground line. So the device 1 receiver line is connected to the transmitter of the second device. Same way the device 1 transmitter line is connected to the receiver of the second device, and the ground lines are shorted with each other. So one device transmitter goes to the receiver of other device, and the other device transmitter comes to the receiver of the first device. So if we see the packet format, so there is going to be a start bit. So start bit is nothing but there is a transition from a logic 1 to 0. So logic 1 to 0 is represented as a start bit. Then we can have a 7-bit data or 8-bit data. This is possible. Then we will be having an optional parity bit which can be used for checking for errors. We can send the data as an even parity or an odd parity, and we can check it at the receiving side, whether the data is properly received or not. Then finally we will be having a stop bit, which is nothing but a low to high transition. So it is just opposite of your start bit. So start bit is high to low transmission, whereas stop bit will be your low to high transmission. So if I take a computer, or if I take a microcontroller, so if I want to transmit letter M, so the ASCII value for this letter M is 10011101. So in order to send this letter M through this UART, first initially we will be having a start bit, which is a high to low transition. So high means here I say it is 5 volt, and logic low means it is 0 volt. So initially we will be having a start bit. Then we have the data bits. So the ASCII value is a 7-bit value, and we will be having that 7-bit data bits. So in the 7-bit data bit, you can see that the LSB bit comes first after your start bit. So after your start bit, you will get the LSB bit, and then subsequently the other bits, and finally you will get the MSB bit. So you will be having 1 0 1 1 0 0 1. So you have to see it from the right to left. So first the LSB, then subsequently it goes on till your MSB. So after all this, we are going to state whether we are going to have a even parity or odd parity. So even parity will be indicated by 0, odd parity will be indicated by 1. So here if you see even parity, in this data I have about even number of ones. If I count the number of ones in this data, I have 4 ones, so which is an even number. So it's an even parity. So we specify the parity bit to be 0 since it is an even parity. And then comes a stop bit, which is low to high pulse. Same way in case of a computer. Okay, if in case of a computer, as I said, the voltage levels is going to change. Logic 1 will be represented by minus 12 volt, logic 0 will be represented by a plus 12 volt. So let us take another example. If I want to transmit the letter J, then the corresponding ASCII value is given by 0x4a, which is 01001010. So here also first we will be having a start bit. So start bit, as I said, it's from logic 1 to logic 0, transition from logic 1 to logic 0. So here we have a transition from minus 12 volt to plus 12 volt. So that indicates the start bit. Then comes your LSB bit. Okay, LSB bit is your 0. So from LSB we try to transmit the data towards left. So thereby we go to MSB. Then we have an optional parity bit. So here if I count the number of ones, we have odd number of ones. So odd parity means it is indicated by 1. Then after this odd parity is inserted into the packet, we will have a low to high transition, which is from plus 12 volt to minus 12 volt. So thereby the data will be in this format in a computer. So you can see two different voltage levels. In case of a microcontroller, the voltages vary between 0 to 5 volt. Whereas in case of a computer, it varies between minus 12 volt to plus 12 volt. So in order to have a compatibility between these two devices, we need to have a driver circuit. So the driver circuit is given by MAX 232. So we have multiple versions like MAX 220, MAX 232, MAX 232A. So this is a IC which is going to have the equaling of this voltage levels between two devices. So when you see this MAX 232, it is a 16-pin IC. So it has a voltage doubler inside and also there is a voltage inverter. So from microcontroller we will get 0 to 5 volt. So this voltage should be doubled, either to plus or minus 9 volt or plus or minus 12 volt, it should be doubled. So we have a voltage doubler, and also we need to have the inversion also, because 0 to 5 volt is transited into minus 12 volt to plus 12 volt. So we should also have a voltage inverter. So both are embedded into this MAX 232 IC. So we will give the TTL inputs from your microcontroller, and the output from your MAX 232 will be your RS232 outputs. So TTL means the voltage levels will vary between 0 to 5 volt. RS232, the voltage levels will vary between minus 12 volt to plus 12 volt. So like that, two types of conversion is possible using this IC. Then here I show a typical capacitor values. We need to connect the capacitor C1, C2, C3, C4, C5. So thereby the corresponding voltage doubling and voltage inverter will happen. So in case of a MAX 232, either you can use the capacitor value of 1 microfarad or you can use a capacitor value of 10 microfarad. So here you see a typical circuit. So in this typical circuit, the transmitter and receiver lines from the microcontroller is connected to T1 in and R1 out of the MAX 232 IC, and the output from T1 out and R1 in is connected to your DB9 connector. So this is a DB9 connector. So this DB9 connector can be connected to your computer. So in computer you will have a male pin. So you can use a female pin to connect to this MAX 232, and this female pin can be inserted into your computer, desktop computer. So this DB9 connector, it comes with the two, one is male connection as well as female connection. So here if you see the pin details, here on the left side I show a male connector. So the pin number 1 is a carrier detect, pin number 2 is receiver, pin number 3 is transmitter, pin number 4 is data terminal ready, pin number 5 is ground, pin number 6 is data set ready, pin number 7 is request to send, pin number 8 is clear to send, and pin number 9 is ringing indicator. So out of this 9 lines, we will be probably using 3 lines. One is receiver line, transmitter line, and ground line. So other signals are handshake signals. If we want, we can use it, or we can avoid using it. So but the 3 important lines which we need to connect is receiver, transmitter, and ground. Similarly, in case of a female connector, the pin numbering will start from right side. So in case of a male connector, it starts from left side, whereas in case of a female connector, it starts from right side. So pin number 1, it goes to 5 towards left. Same way pin number 6 from right towards pin number 9 to left. And the corresponding pin details are shown here. So if we see a typical circuit, we take a microcontroller. So transmitter and receiver lines are multiplexed with your port 3.1 and 3.0. So these 2 lines are connected to T1 in and R1 out of your MAX232 driver. And from MAX232 driver, we get 2 lines. One is T1 out and R1 in. So T1 out is connected to the receiver pin of your DB9 connector. R1 in is connected to the transmitter line of your DB9 connector. And this DB9 connector can be connected to your computer. So now let us look at the program through which we are going to send the data from your microcontroller to the computer. And after receiving the data from the microcontroller to the computer, we are going to send it back to the microcontroller. That is what the program we are going to do. In this, we are going to use IDE, Integrated Development Environment, which is Micro C Pro for AT51. And the simulator which we are going to use is Proteus 8 Professional. So first let me explain the program. So we are going to assign few variables, a character variable, an array R for receiving the data. While receiving the data, we will be receiving the data character by character. So I am going to use an array of 20 elements. So up to 20 elements I can receive the data in this array. Then I initialize a variable I to do a for loop. Then I am going to initialize a variable called as data is received. Once a particular data is received, we can send the data back to your microcontroller. So for that I use a variable called as data received. So now I am going to write 3 subroutines. One is send, initialize the receive variable and the receive subroutine. So in the send subroutine, what we do, we are going to have a string. We are going to have a string which we are going to send it from our microcontroller to the computer. So that starting address location is given by this pointer S. So when this pointer as a valid item, for example hello, so H starting address will be there in your S. So until this hello is transmitted to the PC, so we are going to check this while loop. Okay, while we have a valid pointer, I am going to take that pointer value and put it into the S buffer. So S buffer is something like in a UART communication, we will be putting the data onto this S buffer. So from this S buffer, it will go to the shift register, and the shift register will shift the data out through the transmitter line. So S buffer is something like a storage register. So from microcontroller, the data will go to your S buffer, and from S buffer it will go to the shift register, and shift register will transmit the data out depending upon the baud rate. So we put the data onto this S buffer, then I need to shift this out. So in order for our shifting to get completed, we have a flag called as TI, transmission interrupt. So which is available in your SCON register, serial control register. So if I see this, SCON register, so we have a bit called as TI, transmission interrupt. So this transmission interrupt will be set once the data in the shift register is transmitted out. Same way there is a RI, which is receive interrupt, when a new data is received, this interrupt will be enabled. So we can check this. Once RI is active, then we know that some new data has been received. Then we can read the data. Same way in case of a transmission interrupt, we need to wait until the data is transmitted out. So that is what we do here. Okay, so we are in while scon.ti equal to 0. So until I get ti equal to 1, we will be in this while loop. Once I get ti equal to 1, which means the data is transmitted out. So we can start transmitting the second data. So for that what we do, we again make this ti to go to 0, and then again we will check for this pointer. So the second character will come to your S buffer and it will get shifted out. So this process will continue. So thereby until the completion of our string characters, all the data will be transmitted out. So the concept is simple. We put a data onto the S buffer, then we check for the ti bit. If the ti bit is 1, which means the data is transmitted out, then we put the next data into the S buffer. So thereby again we will check for the ti bit. Once the ti bit is 1, then the data is sent out. So again we will put the next character. So that is how this transmission subroutine works. Then same way we have a receive subroutine. So in receive subroutine what we have to do, we have to check the RI bit, receive interrupt bit. If the receive interrupt bit is 1, then a valid data item is available. So thereby we have to check whether this RI bit is equal to 1. So for that, until if the RI bit is 0, I will remain in this while loop. Once a RI bit becomes 1, I read that value from S buffer, put it onto the array. Then I increment the index, then we set the RI value to be 0 because we have received one data. So we will put the RI value to be 0. Then I am checking whether I have reached the end of my string. So how to check the end of my string? So as soon as I give a string hello, then when I press a enter, which is nothing but a carriage return, right? So carriage return has a value of 13. So I am checking whether enter key is pressed. If enter key is pressed means then the data which we are going to send is completed. So if that is the case, if my S buffer is having the enter keys ASCII value, then we are going to put the data received equal to 1. Else it will be data received equal to 0. So then the second character again, once I get RI to be 1, we try to read that value from S buffer, put it onto the array element. So and this process continues. So here the concept is again same. We check for the RI. If RI is active, we take that value, put it into the array and check whether the string is ended. If the string is not ended, again we go and check the RI. If RI is active, we take the next data, put it onto the array. If the string has ended, so that we try to check it using the enter key. So enter key decimal value is 13. So when the enter key is received, we say that data is received completely. So that is how this subroutine is defined. Same way we have another subroutine called as init R, which is used for initializing your R variable. Once I receive the data, in order to store the next data, I want to clear the data. So for that what I do, we try to initialize a for loop, and in that for loop I am going to put all the elements in the array to be 0. R of I equal to 0. So this is just for initializing your receive array. So after writing these three subroutines, we are going to write our main program. So where I define scon equal to 0x50. So 0x50 means 01, 01, 0000. So this is your scon. So what we put 0101. So which means SM0 is 0, SM1 is 1. So if SM0 is 0 and SM1 is 1, we are in the serial mode 1. So serial mode has 4 modes: mode 0, mode 1, mode 2, mode 3. So mode 1 stands for 8-bit UART. So 8-bit data, and the baud rate is set by the timer 1. Okay, so the number of bits transmitted per second is determined by the timer 1. So I will show how to configure this baud rate. So we are going to set this value to be in mode 1 of a serial port, and then this REN, which is receive enable. So this receiver should be enabled so that we receive the data. So this also is set to 1. So we put 0, 1, 0, 1. So receive enable is also 1, and this RI and TI we are setting it to 0, 0 initially. So that is why this SCON is equal to 0x50. Then we are going to set the TMOD, which is timer mode register, equal to 0x20. 0x20 means 0010 0000. So if you see TMOD, so this is a TMOD. So where I have gate, counter or timer mode, M1, M0, same way for timer 0. So as I said, in mode 1 of your serial communication, we are going to use timer 1. So we are going to use the leftmost 4 bits. So we are going to give 0010. So 0, gate is 0. Here counter or timer is also 0, which means we are configuring it in timer mode. 1 means counter, 0 means timer. So we are configuring it in timer mode. And 10. So M1 is 1, M0 is 0. So 10. 10 means it is in 8-bit auto reload mode. So timer 1 is in 8-bit auto reload mode. So what is 8-bit auto reload mode? So here I have a TLX, timer low register, timer high register. So the content from timer high register goes to your low register, and the incrementation of the value happens of this TLX register. So the incrementation happens to what frequency? It is crystal frequency divided by 12. So if the timer is on, this crystal frequency will be used for incrementing the timer low register content. So we try to increment the value of timer low register content. So once it overflows, the timer flag will be activated. So once the timer flag is activated, again we reload the value from timer high register to timer low register. So this is called as a auto reload mode. So we have a low register, timer low register, timer high register. Both are 8-bit registers. So from timer high register, the data will be loaded onto your timer low register, and the incrementation happens with respect to this frequency, which is crystal frequency divided by 12. So for this application, we are going to use 11.059 megahertz as a crystal frequency. So that frequency will be divided by 12, and that will be used as an incrementation clock. So once my timer overflows, the flag will be set, and we try to reload the value from THX to TLX. So that is what we do here. So we set our timer 1 in 8-bit auto reload mode. So that is why it is defined as 0x20. Then what value we are going to load it to your timer high and timer low of 1? That is determined by the baud rate. So here, in order to set the baud rate to be 9600 bits per second, if I use a crystal frequency of 11.059 megahertz, so how to configure it? So we have to see the PCON bit. PCON bit is nothing but your power control register. So in that power control register, we have the 7th bit, which is your SMOD, which is used for your serial mode. So this serial mode baud rate is defined by this SMOD bit. So it can be used in mode 1, mode 2 and mode 3 of your serial mode. So this I can set it to 1 or I can set it to 0. If this PCON 7th bit is 0, then we use this formula to compute your TH1. If this PCON 7 is equal to 1, then we use this formula to compute your TH1. So depending upon whether my PCON.F7 is equal to 0 or whether my PCON.F7 equal to 1, we compute this value. So for example, I am going to use PCON.F7 equal to 0. So in that case, we use this formula. So we need to have a baud rate of 9600. We know the crystal frequency, which is 11.059 megahertz. So that is given here. So 11.059,000 divided by 384 divided by 9600. So it comes about to be 253. So if I convert this 253 into a hexadecimal value, it is 0xFD. So this is the value which I need to load it onto your TH1, and this TH1 value will get loaded onto your TL1. So that is what we define here. So TH1 equal to TL1, which is equivalent to 0x FD. To get a baud rate of 9600, when pcon is set to 0, at the time we need to load this value. So we have to compute this value. Then we are going to switch on the timer using TR1 bit, okay, which is used for running the timer. Then to send the character from microcontroller to your PC, I am going to use the send subroutine. Send, I am going to send AT89C51 UART. Then in a while loop, I am going to check whether data is received. If the data received is equal to 1, then I am going to send that value. And after sending, we initialize that receive register and I make the data received to be 0. If data is not received, we have to receive the data. So for that we use it in a else. So we call the receive subroutine. So we receive the data. Once the data is completely received, then we send the data to your microcontroller again. So this is a very simple program. Now let us look at the Proteus circuit. So in Proteus environment, we have built this circuit. So here we have a AT89C51 microcontroller. So it is connected with the oscillator circuit frequency. So here we are going to use an oscillator frequency of 11.0592 megahertz crystal. Then there is a reset circuit which is connected to this reset pin. And we are using a MAX 232 IC where the capacitors are connected with the 10 microfarad capacitors. And from port 3.0, the receiver line is connected to R1 out. Transmitter line is connected to T1 in. And the output of your MAX 232, T1 out is connected to the receiver line of your virtual terminal and R1 in is connected to the TXD of your virtual terminal. Since here we are using a MAX 232, the voltage level should be inverted because microcontroller voltage levels will be different, whereas the computer voltage levels will be different. So in order to configure that, right click on this virtual terminal, edit properties. So here you have to select the polarity, transmitter receiver polarity, and I have set it as inverter. So if you are going to transmit the data from microcontroller to microcontroller, you can put it in normal mode. Since I am sending the data from microcontroller to a computer, so it should be in an inverted mode. Okay, so we have to have a change in your voltage logic. So I set it to be in inverted mode. Now let us go to the micro C. So here we have written the code micro C Pro for AT51. So here I have a send subroutine, receive subroutine, and then to initialize your register content. So I have initialized using the subroutine. Then we have the main program. So in the main program, what we are going to do, first we are going to send this character or string from microcontroller to the PC. Then we are going to wait for the response. So then once we send something from your computer, it will be received and that received data will be sent again back. So after receiving the data, it will send the data back to your computer. So from computer, it comes to microcontroller and then microcontroller picks the data and it sends again back to your computer. So once completing this code, we can build this code. So after building this code, we can go and dump that X file into your Proteus 8 environment. So to dump, right click on your IC, edit properties, select the corresponding hexadecimal file. Press open. Set the clock frequency to be 11.0592 megahertz. Press OK. So now let us check the output by pressing this play button. After loading the data, Let us play the play button. So when I press this, you can see whatever data we have transmitted, it has been received here in virtual terminal AT89C51-UART. So now I want to transmit some data from the computer to your microcontroller, and the microcontroller will resend the data. So let me put something like embedded C. So I am going to type embedded C, press enter. You can see the data has been sent back by your microcontroller to the PC program. So next I am going to give something like program. So and I am pressing enter, you can see the microcontroller is sent back. So this is how a data can be transmitted and received using UART. So in this tutorial, I have discussed about how to send a data from your microcontroller to a computer, and after receiving the data in a computer, I can send a data from computer to a microcontroller back. So how to configure the UART, how to set the baud rate of the UART is discussed in this tutorial. So thanks for watching. Please subscribe for more technical learning. Thank you.